Okay, so we did the first way where we have an inertial coordinate system. So now we're going on to the second way. So now we have a rotating coordinate system. But the coordinate system origin isn't accelerating. So in this coordinate system, we're going to use that the acceleration is equal to the observed acceleration. That's the component's double dot. Plus omega dot crossed with P plus 2 omega cross components dot plus omega cross quantity omega cross P. So I think, well, there's sort of two ways you can think of this, like kind of the intuitive way and the mathematical way. The mathematical way is to recognize that the position vector as a function of time is just going to be equal to 0, 0, 5. Okay, that's not just an instantaneous position. The camera is looking at the astronaut the whole way around the circle, right? So this is the observed, for any time, this is the position. And what that means is that take the derivatives of the components and you get 0. And take the second derivatives of the components and you get 0. Also, there's no, it's a constant angular velocity that the coordinate system has. So omega dot is equal to 0. So I said, to me, this is sort of the easiest way to think about it mathematically, like recognize that 0, 0, 5 is actually the position as a function of time. That position vector never changes. But if you also just think of components dot and components double dot as the observed velocity and acceleration, just think about what that motion looks like in that, like in a camera mounted rotating, you know, if with the camera that's rotating on the hinge, it looks like the person just stays there, right? His hair's flying around and stuff, but he's just sitting right there. So if you just imagine that, you know, well, there's no observed velocity and no observed acceleration. And that says the same thing that this says mathematically. Okay, so plug that into the acceleration equation, and you get 0 plus 0 plus 0 for this one because the components dot are 0 plus 0, 0, 5 crossed with 0, 0, 5, Is that the right? No. Those are the positions. So what was it? Positive y, right? Okay, 0, pi 0 crossed with 0, pi 0 cross, and this one's 0, 0, 5. And so you get out of this, well, that's, now you recognize that that's the same cross product we got from a different way here. So you get 0, 0, negative 5 pi squared. And so Newton's second law says the force on the astronaut by the chair plus 0, negative 588.60 is equal to the mass times the acceleration, 0, 0, negative 5 pi squared. And so FAC is the same thing we got before, 0, 588.6, and then negative 300 pi squared. Any questions about that one?
So let's say we were talking about a lot of things, the speed, not the speed.
Yeah. Well, you just have, yeah, you wouldn't have as many zero terms here. And we'll do, well, we'll do one, what do I have here? Yeah, let's do one like that.
In this case, in the observed velocity, how is it moving zero? The camera's moving with
The observed, if the camera is moving,
on the hinge and spinning, when the velocity would always be zero. The observed velocity.
yeah, in this case, right, right. But if you're trying to track the motion, so you could imagine like if,
So the y-axis is rotating in this situation too. So the z was staying with the arm, but the y is staying with this.
the y is straight up, so that's just,
Oh,
that's not changing, but x and z are changing. So yes, in this case, the yeah, there's not going to be any observed velocity or any observed acceleration, but you could imagine the astronaut holding a fish and the fish is swimming around or whatever. And then in that rotating camera, you'd have some observed velocity of the fish, you know, and then that goes in for the p dot and the p double dot. And then, so it's not like generally like those are going to be zero in any problem. In this one it is, yeah. Right. Yeah, exactly. Yeah. Right. What? Yeah, exactly. So that's, yep, that's when you're going to use this most often. When you have some simple motion going on that's easy to describe inside another motion. It's hard, it can be hard to describe them all together, but easy to set it up in this format. All right, so now the third way. So this time we have coordinate system fixed on the chair. And so we have an accelerating origin and rotating axes. So in this case, we need to, basically we need to think of the acceleration of the astronaut relative to the ground. That's what we're trying to find. Okay. Is equal to the acceleration of the astronaut relative to the origin plus the acceleration of the origin relative to the ground. This is going to come from our new equation. You know, this is going to come from the rotating coordinate system axes equation. And then this is, you know, we're going to have to come up with that separately, but it's an easy, so what's the form that the acceleration of the origin relative to the ground is going to take, or what kind of motion is the origin in? It's just in a uniform circular motion, so that's just calculating a centripetal acceleration. Okay, so so let's go through this. So the acceleration of the astronaut, so we're getting this piece. It's equal to components double dot plus omega dot cross P plus 2 omega cross components dot plus omega cross P. All right, so in this coordinate system, can you imagine, so let's go back to the picture. Can you come up with mathematically what the position vector of the astronaut is as a function of time? It's 0, yep. So the position vector for any time is 0. And that means that the observed velocity is 0. And that means that the observed acceleration is 0. And so now, like, this messy formula is going to get really simple. So everything's 0. This one's 0 because the observed acceleration is 0. This one's 0 because it's 0 cross 0. This one's 0 because the observed velocity is 0. This one's 0 because the position vector is 0. But now we have to add this to the acceleration of the origin with respect to the ground. Okay, so what's that? So the acceleration of the origin with respect to the ground, that's a circular motion. So what's the omega of that circular motion? Well, okay, so this is a circular motion, so we can think of it as alpha cross r plus lowercase omega cross omega cross r. What's alpha for this circular motion? 0. What's omega? 0, pi, 0. Crossed with 0, pi, 0, cross. And now, what's r? R is a vector from the center of the circular motion to the point. So that's going to be 0, 0, 5. And so you get 0, 0, negative 5 pi squared. And so the final answer for the acceleration of the astronaut is 0 plus 0, 0, negative 5 pi squared. Same thing as we got the other two ways. And so add them all to go through Newton's second law. And you get that the force on the astronaut by the chair is equal to 0, 588.6, negative 300 pi squared. So I think this is a nice one to go through to make sense out of all the R's and P's and stuff. Like, I would recommend, after the test, probably spend some time going through this and making sure you understand why the things are zero that are zero, where you put this value and that value. But I think for the most part, like any problems that we're doing now, you can do, well, you can at least do two ways. And often you can do it all three of these different ways. So that's sort of a nice thing. You have a way to kind of check your answers at the same time that you're reminding yourself about the circular motion and rigid body motion. All right, so if you can always do, I mean, I think now this brings up sort of a interesting question. If you can always do problems, so these problems with a rotating coordinate system, if you can always do them, solve the same way with an inertial coordinate system, just using rigid body motion, is there really any reason, like is it really ever helpful to do these problems this way, or is it just kind of like a mathematical, muscle flexing type thing? They wouldn't be, right? So, but like all that stuff, like why wouldn't you just set it up in an inertial coordinate system and solve it using rigid body motion, and then we wouldn't even have to discuss this topic? It does make you look smarter, and that is useful. But also, a lot of times, I mean, you don't have full control in a real problem of where your data comes from. Like, for example, like say that so if we're measuring celestial data from Earth, we don't, like in a problem like this that you're designing, like it's a lot easier to say, okay, imagine, how about instead we just fix it to here, Or how about instead we fix it to something fixed? But if you're really getting data, putting a camera on the Earth is and measuring it is relatively easy. Putting it out in space on a fixed, like that's a lot harder. That's a lot logistically more difficult to do, you know? So yeah, like what you use as your coordinate system is determined by where you can put your measuring device, you know? And so there are a lot of problems. So even though, I guess what I'm saying is, as you're going through these problems, it might occur to you like, well, I could always do these problems in an inertial coordinate system. Why wouldn't I just do that? But in real problems, your data has to come from setting up equipment, you know, and where you set up equipment has a big effect on how easy or hard it is to get data, you know. And so if it's easier for you to take measurements in a rotating coordinate system, it's a really useful tool to be able to apply, you know, make these corrections and then use that in laws of physics. So since all of these examples are kind of, you know, cooked, it makes it seem like it's not useful, but in fact, like in real problems, being able to use a variety of different coordinate systems is super useful. Any questions about that example or anything related to this stuff before we go on? I guess let's do, I think we have just enough time to do. So I want to show one thing that I think is kind of cool. I mentioned this last time. I'm going to apply this to polar coordinates and show where those crazy expressions for velocity vector and acceleration vector in polar coordinates come from. Okay, so if you're tracking a particle in polar coordinates, so you have this, let's think of this as sort of an implied ground frame. This coordinate system is inertial. And your particle is doing this. And you're tracking its motion by keeping track of the distance from this implied coordinate system to the particle. That's your r. And an angle theta. Okay. So the first thing you have to notice is your polar coordinates you're used to thinking of it in terms of r theta, but that's not a vector. That's not the position vector in polar coordinates. Yeah, right. So in order to come up with a position vector, you need a orthogonal coordinate system. That's not the position vector in polar coordinates. So instead, to get the position vector, you need to define an orthonormal coordinate system. And so we're going to define the r-axis this way. Call that ER. And then we're going to define the E theta axis perpendicular to that. And so in this coordinate system, what's the position vector of the particle? Well, how far do you have to go in the ER direction to get to the particle? R. And then how far do you have to go in the E theta direction to get 0? Yep. So this is just R ER plus 0 E theta. Or I'll write this as components R0. So notice that this coordinate system rotates, right? As this particle moves around, the ER axis keeps aiming at the particle, and so this thing rotates back and forth. Can anyone think of an expression for the angular velocity of this coordinate system? Well, its angular position is theta, so its angular velocity is theta dot, and that's in like a third perpendicular axis. So I'll think of that as 0, 0, theta dot. And so now all we have to do is apply the formulas for velocity and acceleration in a rotating coordinate system. So the velocity vector is, so that's components dot plus capital Omega cross with the position vector. What are the components dot? Well, the position vector is this, and that r can change, right? R isn't a constant. So this is going to be r dot 0, 0. We're going to add that to 0, 0, theta dot crossed with the position vector, r 0, 0. And this cross product is r theta dot in the y direction. So you get r dot, r theta dot, 0, or, you know, that z component isn't something that we talk about. It's not something you talk about in polite company. Okay, so that's an expression for the velocity vector in polar coordinates, and you've seen that formula probably somewhere. Maybe you derived it a different way. There's another way to come up with that doesn't involve this rotating coordinate system thing. But here's sort of a nice, simple way of deriving this velocity vector. And now we can use the acceleration formula to derive an expression for the acceleration. So that's components double dot plus omega dot cross position vector plus 2 omega crossed with components dot plus omega cross P. All right, so for the components dot, our position vector is R0, 0. So what's components double dot? Remember, well, that R, I mean, we don't, that could be infinitely differentiable as far as we know. That R can change. So that's just going to be R double dot and then zeros. Our omega is 0, 0 theta dot. So what's omega dot? That's right. So this is 0, 0 theta double dot crossed with position R0, 0. This is 2 times 0, 0 theta dot crossed with components dotted is R dot 0, 0. And then plus 0, 0 theta dot cross quantity 0, 0 theta dot cross R0, 0. And you get, you can go through that if you want later, but what you get out of this is R double dot minus R theta dot squared. That's your R component. And your theta component is 2 R dot theta dot plus R theta double dot. And so again, that's like a formula you've probably seen before, but this is an easy way to remember how to derive it. Any questions about that? Okay, so I'm going to go right now. I have office hours right now, but I'm going to put up the new third problem for linkages, and I'll get the solution up as soon as I can too. And yeah, that's it. Test tomorrow.